Diode capacitance means the diode exhibits the property of capacitance. As you see, you have forward bias capacitance, and in reverse bias also you can observe the capacitance property. In reverse bias mode, whatever the capacitance you see, you term it as transition capacitance and you indicate it as CT. In forward bias mode, whatever the capacitance exhibited by diode, you represent it as CD, called as diffusion capacitance. Now let us go with the first capacitance, which is transition capacitance. So let us take a reverse bias diode. As you see in this picture, you have a reverse bias diode. Reverse bias diode means you are applying negative to p-type material, positive to n-type material. For a no bias diode or an open circuited diode, you will see a depletion layer at the junction already with some barrier potential. But as you have applied some voltage which will reverse bias the diode, what happens? The depletion layer which is seen at the junction is widening, so that the depletion layer width is increasing. So this depletion layer, which will not be equal to 0 at any point of time, you treat the depletion layer which is formed as a capacitance, as parallel plate capacitance. The two ends of the depletion layer, you treat it as parallel plates of the capacitor. And the field, what field is formed here? The field which is due to donor ions, acceptor ions. So the field which is formed at between the two ends of the depletion layers, that field is like the field in a parallel plate capacitor. So now that capacitance value you are deriving. So for that we have different types of diodes. For all the diodes, whatever it is, if you say capacitance, you can simply define with equation 1 as we have given. So this equation 1 is C is equal to dq by dv. It's a known equation. The same similar equation we will take, but we have to derive what is Q value here for this diode, so that we can get what is capacitance value. So first we will go with what is the structure we are taking for deriving this transition capacitance. Now, actually, while manufacturing a diode, you have different constructional process like ground junction or fusion junction or alloy junction. You have different types how you can manufacture a diode. Let us take one type among them. We have chosen alloy junction. So this alloy junction, how it is made? You are taking an n-type germanium bar. So as I am showing in the picture, it's completely an n-type germanium bar. Let us consider. On one side of this n-type germanium bar, now you are placing a third group or a trivalent impurity, which is indium, on one side of this particular n-type germanium bar. So you are placing an indium dot, a material which is of trivalent impurity, you are placing on this n-type germanium bar. You are moving this combination to higher temperatures. What happens? Definitely the indium material will be melted and it will dissolve into this n-type germanium bar. When it dissolves, it tries to change some part of this n-type germanium bar into p-type material. But actually in the n-type germanium bar, electrons are more in number. Your trivalent impurity have holes. Now these holes, they recombine with the electrons while it is combining with the n-type germanium bar. So they will disappear in the form of heat. Then what are left over? So electrons have disappeared because of recombination due to the indium holes what you have added to this n-type germanium bar. So whatever holes which are left over in the indium material are there in this p-type material. So you can say the hole concentration is very, very lesser than the electron concentration in the n-type semiconductor. As I am showing in this picture, here I have shown equal concentrations both in n and p-type regions. So because of that, the depletion layer is also equally distributed. The width of the depletion layer in both n-type and p-type is equal. But if you see in this picture, the width of the depletion layer here is different with respect to the width of the depletion layer in this region. Why? Because the hole concentration here is very, very lesser. The electron concentration is very high here. So then you can ask why, if the concentration is lesser, then how the depletion layer width will be wider. Here, if you observe, when you apply some voltage, the electrons from N type has to move into P type so that it can widen the depletion layer. As your holes were scattered, they are not nearer to the junction. The electrons has to move deeper into this P-type region. That means they have to move far away from the junction and they have to reach those holes. So as they are moving far away from the junction, similarly the depletion layer width is also occupied more region in the P-type layer. But when the holes try to move into this N-type region, you see readily available electrons because the concentration is more nearer to the junction. Because of that, they can recombine nearer to the junction, whatever the charge carriers which are found. So you see the depletion layer which is formed in the N-type region is very, very less in width when compared to this P-type region. So this is about alloy junction. So you take a N-type germanium bar, you place an indium dot on it, that means indium material on it, so that you can convert some part of the N-type material into P-type material. So as it has converted into P-type material, it forms a PN junction. Now when you see the physical structure of this PN junction, the depletion layer which is formed is not equally distributed on both sides of the junction. So that depletion layer width have a difference in the P and N-type layers. That is what I have indicated in this equation, where WP means width of the depletion layer in P-type region is much higher than the width of the depletion layer in N-type region. So this is about alloy junction. Now, as you know about the width, let us also talk about the concentration levels. You have discussed about the x-axis. That means this x-axis is saying that the width of the depletion layer is more in P-type than the width of the depletion layer in N-type. Now let us move to the y-axis now. What is this y-axis? This y-axis is representing the concentration. What concentration? Whatever the field which is formed at the depletion layer, you are concerned about the concentration. You see donor concentration in this N-type material, acceptor concentration in this P-type material. So how is donor concentration represented? ND. That means it is a positive field which is formed in the N-type region nearer to the junction. Similarly, acceptor concentration is NA, which is indicating a negative field which is formed in the P-type layer nearer to the junction. If you check these concentration levels now, as more electrons are there in this N-type region, you see definitely number of holes is equal to the donor concentration. Number of electrons is equal to donor concentration. Number of holes is equal to acceptor concentration. You see same type when you have seen extrinsic semiconductor. In a P-type semiconductor, you have holes, you have acceptor ions, which is both the concentrations are same. Small p is equal to Na. Similarly, in N-type semiconductor, whatever the concentration of electrons you see, N, small n, is equal to Nd, which is donor concentration. So as the number of electrons are more when compared to holes, here also donor concentration is more. So in the y-axis, you see higher concentration than the acceptor concentration, what you see here. So this level is very less in number, that means the concentration is lesser value than the donor concentration. So this donor and acceptor concentrations are different. So if this is donor concentration, then this is your acceptor concentration. So you see a difference in the y-axis level. So now that is what I have indicated with this equation. I hope you are seeing the down equation below this. So this equation is describing you about the width. This equation is describing you about the concentration. This is y-axis, this is x-axis. Now, once you have got your diode alloy junction and you have biased it, you have a constant depletion layer. But you should have a particular thing where it is electrically neutral. Electrically neutral means the net charge must be equal to 0. So you are equating this value where Na into Wp is equal to Nd into Wn. What is this Q? Q is a charge. Okay, so this is Na, concentration into width, concentration into width. So as this holds good, this will also hold good because Na is lesser than Nd and Wp is greater than Wn. So this equation holds good for this alloy junction. Now, what I need actually for this junction, I need to derive what is this transition capacitance. So I want to derive Ct means this Ct value should be, which is dq by dv. So I should get what is Q value. What is Q? You have got charge density value. What is the net charge? But you need to find out what is charge value so that I can differentiate with respect to voltage and I can get what is capacitance value. So let us see that equation. So I am taking a Poisson's equation here so that I can get a particular value which is derived as dw by dv. Rather than explaining this, let me show you first what is Ct, then you can understand. So in the previous slide, what we have seen is this value. I want charge value. This charge Q is equal to whatever the charge density, what you have seen, multiplied by the area. Now, if I want capacitance, differentiate this Q value with respect to voltage. What you will be getting? This value, Q, in the upper equation, what you are seeing there, Q, Na into A, dW by dV. If I want transition capacitance, I need to derive what is dW by dV. But what is dW by dV? To derive this equation, I am taking Poisson's equation. What is Poisson's equation? It is relating potential with charge density. What is potential? How it is related with charge density? Actually, you know this equation previously. There is no need of derivation here. We will be directly taking the Poisson's relation and we will be getting what is dW by dV. So here it is relating the potential with the charge density. So if you see the fourth equation is showing d square V by dx square, which is equal to Qna by epsilon. Now that fourth equation, when you integrate it twice subject to boundary conditions, then you can get the value of V. V is equal to Qna x square by 2 epsilon. But this is the general equation. You need to imply to your alloy junction. In your alloy junction, what is X? X is a width. So if I substitute width as WP, means WP plus WN both together. But as WP is much greater than, as WP is much greater than WN, you can simply neglect WN and you can replace WP plus Wn as Wp, which is giving the whole width of the depletion. And voltage V as Vv, or you can simply leave it as V also. It is one and the same. Now, replace the terms in the fifth equation. You will be getting Qna W square by 2 epsilon. So this is your sixth equation. So this sixth equation, it shows the relation between the voltage and the width of the depletion layer. How they are related? Width is proportional to square root of voltage. This is an actual important bit. You will be getting few problems also. So this is an alloy junction. Alloy junction V is proportional to W square. If I have changed the diode, if I take a ground junction for an example, it's another type of how you make it. You will be continuously adding third and fifth group elements to a pure silicon material to get a ground junction. So if I take that type of ground junction, then in the sixth equation, V is proportional to W cube, width cube value of the width of the depletion layer, or W is proportional to cube root of V. What I have indicated here. This equation is showing width is proportional to square root of the V value, whatever the voltage you have applied, or the barrier potential what you are seeing. But if you see ground junction, this will be cube root of the voltage. Fine. So now let us take the sixth equation and you differentiate with respect to the voltage. What you will be getting? This is dV by dV. So it is 1 is equal to QNA by 2 epsilon, constant value. Differentiate W square with respect to dV. What you will be getting? 2W into dW by dV. Now rearrange the equation so that you will get what is dW by dV. So if we rearrange the equation, 2 gets cancelled. Leftover terms are dW by dV is equal to epsilon by QNA W. So this is the equation what you have derived, which is dW by dV. For this you need Poisson's equation, because when you want to calculate transition capacitance, you see a term which is dW by dV. To calculate dW by dV, you have gone for Poisson's equation and you have derived what is dW by dV. Now you have got dW by dV, substitute in transition capacitance 7th equation. When you substitute it, QNA gets cancelled. Leftover terms are epsilon A by W. So epsilon is epsilon R into epsilon naught, which is relative permittivity, absolute permittivity. A is the area of the depletion layer. That means field, which is in between the capacitance plates, two ends of the depletion layer. W is width of the depletion layer. So as width of the depletion layer increases in a reverse biased diode, the transition capacitance decreases. This is about transition capacitance. As we have said in transition capacitance, there was a depletion layer. So directly you can take that depletion layer acts as parallel plate capacitor. But what happens in forward bias? As you apply the voltage, you will not see any depletion layer. The depletion layer becomes 0 and you see conduction through the material. Then how you can derive the capacitance value? Here, you are more concerned about the injected carriers or the net charge which is induced into the n-type region. So this net charge value, what is induced into this, which is nothing but the whole concentration. So you are concerned about Q value, which is defined by the whole concentration P in the n-type material. So this is Q value for a forward biased diode. Now you differentiate this with respect to voltage, because you want dQ by dV. Differentiate this with respect to voltage. What you will be getting? CD is equal to dQ by dV, which is equal to, what are the terms you see? A, Q, LP, all are constants, into what is the constant charge value? Pn of 0. So you can differentiate this value, which is dPn of 0 by dV. If I want diffusion capacitance CD, then what I should derive? I should derive what is dPn of 0 by dV. If I get this value, then I can get what is diffusion capacitance value. So let us derive this value first. How I can derive this value? Did you see this equation? Did you see this term in any of the diode equations? Yes, we have seen this term in diode current. If you want me to show the previous equations, so this is a diode current equation, the whole current value. So I can take this equation directly to derive that term. So I have taken the term, I have taken the current value. Again, I have represented the equation, which is representing the whole current. So this process is totally for what? To derive, if you see the heading, it is to derive dPn of 0 by dV. You are differentiating the whole concentration with respect to the applied voltage. Now, if I want this value at x is equal to 0, I have taken current value, and at x is equal to 0, you can substitute it as AQ dP by LP. Leftover term is Pn of 0 into e to the power of minus x by LP. If x is equal to 0, then it is Pn of 0. Now this equation, third equation, differentiate with respect to voltage. What you will be getting? This is di by dV, which is equal to, what are the terms? AQ dP in the numerator by LP into, what is the leftover term? Which is dp n of 0 by dv. So this is a term when you have differentiated with respect to voltage. What you need this term. So this term, rearrange the equation to get this term. When you have rearranged this equation, you can get this equation move to the left hand side. So this I can bring to the right hand side. So what is left over? dpn of 0 by dv is equal to LP cross multiply by AQ dp into di by dv. What is di by dv? What is dv by di? It is dynamic resistance small r. If it is di by dv, it is 1 by r. 1 by r means conductance. So you are representing conductance value G. If it is static value, capital R, capital G. As you are representing dynamic value, that means dV by di, you are representing it as R. It is 1 by R value. So di by dV is 1 by R. 1 by R, I am indicating it as G value. So now, as you have got what is dpn of 0 by dV, now you substitute in second equation. What is the second equation? The CD value. So this CD consists of this term. I got the value now. So the fourth equation gives you what is dpn of 0 by dV. So substitute dpn of 0 by dV, which is LP by AQ dp into G. Substitute the value. Cancel the common terms. Left over is LP square into G by dp. Let me continue with the same equation. What is the equation? CD is equal to LP square into G by dp. But LP square by dp, that means diffusion length, dp is diffusion constant for holes. If it is for electrons, Ln dn. So that is termed as mean lifetime of holes. What do you call it as? LP square by dp is represented as mean lifetime. That means once holes have entered into, let me explain you with the diagram. Once holes have entered into this n-type region, let us take one hole out of 100 holes. They have entered into this n-type material. Whether that hole will move to the end of the material or in between, it may recombine with the electron. How much length it can diffuse? It is called LP. And the constant, that means proportionality constant, is dp. What you call how much time it can stay? What is the lifetime? Or before recombination, before the charge carrier is dead because of recombination, what is the lifetime of that particular hole? Is termed as tau. So this you call it as mean lifetime of hole when it has entered into opposite material. So now that is defined as LP square by dp is represented as tau. So that CD is equal to tau into G. What is G? G is again 1 by R. It is simply rearranging the equations. You can use any of these equations, only you are rearranging the equations in the place of G as 1 by R, and again R is equal to dynamic resistance you have derived, which is eta Vt by I. So I can substitute the value. So what is CD? CD is this equation, tau I by eta Vt. Or you can substitute tau G. That means G is equal to 1 by R. What is 1 by R? I by eta Vt. Either you can substitute this equation or you can make it as tau by R, substitute R equation, and you can get what is CD value. CD value is tau I by eta Vt. This is diffusion capacitance. Or you can also say from this equation, CD is equal to tau by R, or tau is equal to CD into R. R into CD is equal to tau. So you can rearrange the equations. In the problem, you may be given any of these values and you have to derive other parameters. So this is about diffusion capacitance. For diffusion capacitance, there is no depletion layer as in transition capacitance, because transition capacitance is for a reverse biased diode. Diffusion capacitance is for a forward biased diode. So you are much concerned about the injected carrier concentration from N region, P region to N region. Here you are considering holes. You can also do the same process with electrons too. You can go with either hole concentration or electron concentration, but they should be the minority carriers which are in the opposite layers. So this is about transition and diffusion capacitance values. So once you have derived transition capacitance, which is for a reverse biased diode, Ct is equal to epsilon A by W. And diffusion capacitance, no depletion layer, you are deriving the charge with the injected carrier concentration and using the whole current, what you have derived in the diode equation, you are getting the required terms, substituting these values, and you are getting Cd as tau I by eta Vt, or Cd is equal to tau G, or it is tau by R. R into Cd is equal to tau. So this is about transition and diffusion capacitance.